When you think about AI today, I mean, whether it's the latest generative models crafting these incredible images or, chatbots having surprisingly human-like conversations,
Hmm?
have you ever stopped to wonder where it all began? Like, who laid the very first bricks of this monumental edifice, defining its very foundations?
It's so easy to get caught up in the current breakthroughs, isn't it?
Yeah.
The rapid pace of innovation we're witnessing now is just staggering. But it's really vital to remember that the intellectual groundwork for all of this was poured decades ago by some truly extraordinary minds.
Yeah.
These aren't just historical footnotes. They are, the bedrock upon which everything else is built.
Absolutely. And today we're taking a deep dive into the life and profound legacy of John McCarthy. Now, that name might not be as universally recognized as some modern tech giants, maybe, but his influence on artificial intelligence is quite simply unparalleled. He didn't just contribute to AI, he was truly its principal architect. I mean, shaping its very name, its foundational tools, and even its philosophical direction. He really provided the intellectual compass for a field that would, decades later, transform our world.
And what's truly fascinating here, I think, is that McCarthy was far more than just a brilliant technologist. He was a strategic visionary. He understood the fundamental need to actually define and nurture and institutionalize a completely new field for it to truly flourish.
Right.
He wasn't just solving problems, he was building the whole ecosystem for future solutions.
That's a critical point. So our mission for this deep dive, then, is to unpack his intellectual journey. We'll trace his path from his deeply mathematical roots right up to his pivotal role in creating the field's defining moment. We'll explore his groundbreaking technical innovations like a programming language that profoundly changed how machines thought, you could say, and a conceptual leap that really paved the way for modern cloud computing.
Yeah, that's a big one.
And we'll delve into his relentless pursuit of formal logic to teach machines common sense, which is still a huge challenge today, right?
Oh, absolutely.
Most importantly, we'll try and connect the dots, see how his ideas, conceived decades ago, continue to resonate deeply, and maybe even offer surprising solutions for the cutting edge of AI research today. Okay, let's unpack this. So, John McCarthy's path to becoming the architect of AI, it began with a remarkably rigorous academic foundation, really firmly planted in the world of pure mathematics.
Right.
He was born in Boston, Massachusetts back in 1927, and apparently his intellectual prowess was evident very early on. He actually earned a Bachelor of Science in Mathematics from Caltech in either 1947 or 1948.
Caltech, wow.
Yeah. And here's a fascinating detail from his early academic life, which perhaps speaks volumes about his priorities. He was even temporarily suspended from Caltech for failing to attend physical education courses.
No kidding. PE.
Yeah. He then served a brief stint in the U.S. Army, got readmitted afterwards. But this anecdote, while it seems minor, it really suggests a kind of single-minded dedication to intellectual pursuits that defined his entire career, doesn't it?
It really does.
Hints at a mind already fully immersed in abstract thought.
That detail is quite telling, isn't it? It almost sounds like a character from a movie. Prioritizing abstract thought over like mandatory gym class. It really sets the stage for a career defined by pure intellectual pursuit.
Exactly.
He then went on to receive his PhD in mathematics from Princeton University in 1951. His dissertation was titled Projection Operators and Partial Differential Equations. Pretty heavy stuff.
Sounds it.
But the truly pivotal moment in his early intellectual development, as the sources highlight, was attending a lecture by none other than John von Neumann at Caltech.
Von Neumann, wow. That's a huge name in computing.
Huge. Von Neumann, a polymath known for his groundbreaking work in quantum mechanics, functional analysis, economics, and, maybe most relevantly here, the architecture of modern computers. He profoundly inspired McCarthy's future endeavors in computing and intelligence.
So it wasn't just a lecture, it was like a spark.
Exactly. It was a spark that ignited his interest in the very foundations of computation and, well, intelligence itself.
So what does this deep mathematical background, degrees from places like Caltech and Princeton, what does that tell us? Not just about McCarthy, but about the very nature of AI's origins. Was it always destined to be so mathematically rigorous, or did his background maybe uniquely steer it in that direction?
That's an insightful question. This deep mathematical background really underscores that AI, from its very inception, wasn't just some narrow subfield of computer science, as we might sort of perceive it today.
Right.
It was a profoundly interdisciplinary endeavor. It drew heavily from mathematical logic, theoretical computation, even early concepts from cognitive science. His doctoral advisor, for instance, was a mathematician, which really cemented this orientation.
So it was baked in from the start, in a way.
Yeah, this foundational blend, particularly his emphasis on formal logic and abstract symbol manipulation, it profoundly shaped the symbolic AI paradigm he championed. It established a rigorous, mathematically driven path for exploring intelligence. And that really distinguished his approach from other computational models that were emerging at the time, things like neural networks or cybernetics. He brought this fundamental belief that intelligence could be formally captured and manipulated. And that belief was really rooted in his deep understanding of logic.
Beyond his individual brilliance, though, McCarthy was also, as you said, a master institutional builder. After his PhD, he held short-term appointments at Princeton and Stanford. Then, from 1955 to 1958, he was an assistant professor of mathematics at Dartmouth College.
Yeah, Dartmouth.
And this period was absolutely crucial because it was there, at Dartmouth, that he organized the seminal Dartmouth Summer Research Project, which, yeah, we'll definitely dive into more detail about very soon.
Indeed. And following his pivotal time at Dartmouth, he moved to MIT in 1956, served as a research fellow and faculty member until 1962. It was at MIT that he co-founded the MIT Artificial Intelligence Project.
Ah, okay.
And apparently quickly became affectionately known as Uncle John by his students, which I think is a testament to his approachable and maybe nurturing leadership style.
That's nice.
Then in 1962, he became a full professor at Stanford University. He'd remained there until his retirement in 2000, eventually becoming professor emeritus. And his time at Stanford was immensely impactful. He founded the Stanford Artificial Intelligence Laboratory, or SAIL, there.
Yeah, that's legendary.
It swiftly became one of the leading centers for AI research globally.
So McCarthy wasn't just inventing stuff. He was actively creating the environments for AI to grow. His role in founding and leading these AI labs, it demonstrates a profound understanding, doesn't it? That for AI to evolve from just an idea into a robust scientific discipline, it needed dedicated institutional homes.
Absolutely.
It needed sustained funding and, crucially, a critical mass of researchers all working together. It's one thing to have brilliant ideas. It's quite another to build the infrastructure for an entire field to thrive.
That's a critical point. His foresight really cultivated this competitive yet collaborative ecosystem for AI research. The sources specifically mention MIT's Project MA and Stanford's SAIL as friendly rivals.
Friendly rivals, I like that.
Yeah, it wasn't destructive competition, but a healthy one that really spurred innovation and pushed the boundaries of what was thought possible. These labs became incubators for talent and ideas. They fostered an environment that led not only to significant advancements, but also to hotbeds of entrepreneurial activity, as the sources put it.
Hotbeds, okay.
Yeah, and numerous corporate spin-offs. We're talking about influencing companies like Microsoft, Sun Microsystems, Amazon.com, Cisco Systems down the line.
Wow.
This demonstrates a clear understanding of how to translate fundamental research into tangible, real-world impact, and to basically foster an entire industry.
It's clear his individual contributions and that institutional vision were recognized with the highest honors throughout his career. So what does this really impressive array of accolades tell us about his lasting legacy?
It means his influence was just monumental and widely acknowledged across the scientific and technological communities. He received the Turing Award in 1971.
The Turing Award, yeah, that's the big one.
It isn't just an award. It's considered the highest honor in computer science, often called the Nobel Prize of Computing, and receiving it just 15 years after coining the term AI. That speaks volumes about how quickly his peers recognized the foundational shift he initiated.
15 years, wow.
Then in 1990, he was awarded the United States National Medal of Science. That's a recognition not just for technical brilliance, but for broader national impact, a testament to how his work shaped the technological landscape of the country. He also garnered the Computer Pioneer Award in '85, the IJCAI Award for Research Excellence, also in '85, the Kyoto Prize in '88, which honors significant contributions to the scientific and cultural betterment of humankind. And his final major accolade was the Benjamin Franklin Medal in Computer and Cognitive Science in 2003.
So a lifetime of recognition.
Absolutely. These accolades collectively confirm his foundational status and unparalleled lasting influence in computer science, and specifically in artificial intelligence. He passed away in 2011 at the age of 84, leaving behind a truly unparalleled legacy that continues to shape our understanding of intelligence itself.
Now let's talk about the actual birth of AI as a field. The formal inception of artificial intelligence as a distinct scientific discipline is just inextricably linked to John McCarthy's vision and initiative. particularly through one pivotal event, the Dartmouth Summer Research Project on Artificial Intelligence.
This 8-week workshop, held at Dartmouth College in the summer of 1956, is widely regarded as the foundational event of artificial intelligence as a distinct field. It's frequently referred to, and I think quite accurately, as the Constitutional Convention of AI,
The Constitutional Convention of AI, I love that.
because it truly defined the field's initial charter and gathered the founding fathers, so to speak.
Imagine being in that room, defining whole new scientific discipline. What do we know about the atmosphere in that small Dartmouth college in the summer of '56? Was it like intense debate or more of a unified vision unfolding?
Indeed. Well, while we don't have a minute-by-minute transcript of every single discussion, what's clear from historical accounts is this shared sense of profound possibility and just audacious ambition. The project was formally proposed in 1955 by John McCarthy, who was then an assistant professor of mathematics at Dartmouth. He collaborated with Marvin Minsky, Nathaniel Rochester, and Claude Shannon, all giants in their own right.
Huge names.
But it was McCarthy who really took the lead in writing the proposal and organizing the event. They gathered not just to brainstorm, but to formalize a belief that every aspect of learning or any other feature of intelligence could, in principle, be so precisely described that a machine could simulate it.
That's a bold claim for '56.
Incredibly bold. That conjecture in itself was a kind of declaration of war against the impossible, really setting the trajectory for decades. And here's a truly key fact. The proposal itself is credited with introducing the term artificial intelligence.
Ah, so that's where the name came from.
That was the moment AI became formally recognized, distinct from other computational pursuits, setting its trajectory for decades.
And his decision to name the new field artificial intelligence was more than just a convenient label, wasn't it? It sounds like it was a deliberate and strategic choice, partly driven by a desire for maybe neutrality and precision.
Exactly. He aimed to avoid the narrower focus of automata theory, which was mostly concerned with mathematical models of computation, and also the heavy emphasis on analog feedback associated with cybernetics, which was a broader field studying control and communication in animals and machines.
Right, Norbert Wiener's field.
Precisely. He also wanted to avoid potential conflicts with prominent figures like Wiener. McCarthy's motivation really stemmed from a disappointment with existing research that he felt didn't adequately explore the true potential for computers to possess intelligence beyond just simple behaviors. He sought to clearly define a field focused on constructing machines that acted in a truly intelligent manner, not just by mimicking, but by reasoning.
So this wasn't just a label, it was a profound statement of intent.
Absolutely. The coining of artificial intelligence was a strategic maneuver to define and legitimize a new scientific discipline. By deliberately choosing this term, McCarthy differentiated it from existing narrower fields. It provided a clear aspirational identity for the nascent field that served as a kind of beacon for subsequent generations of computer scientists and researchers.
That clarity must have been crucial.
Oh, absolutely crucial for attracting dedicated researchers, securing funding, and establishing a cohesive research community focused on this shared grand challenge of building intelligent machines. McCarthy himself even recollected having a vague feeling he had heard the phrase before, but was never able to trace its origin,
Interesting.
suggesting a term that was perhaps intellectually in the air, but which he firmly captured and formalized.
The Dartmouth proposal articulated that truly profound conjecture that became a guiding principle for so much of early AI research. Every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. That's an audacious claim for 1956, suggesting a remarkable optimism and a kind of blueprint for how they envisioned machines could achieve intelligence.
It certainly was. The workshop aimed to explore how to enable machines to use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves.
Ambitious goals.
Incredibly ambitious. The discussions were wide-ranging and incredibly prescient. They covered areas like natural language processing, neural networks, theory of computation, abstraction, creativity, topics that are not only still highly relevant to AI today, but are really at the absolute cutting edge of current research.
So they basically laid out the roadmap right there.
In many ways, yes. This gathering, despite its modest scale, effectively laid out the entire ambitious roadmap for the field of AI for decades to come.
What's fascinating here, though, is that this foundational conjecture, while it was incredibly inspiring and instrumental in launching the field, it also subtly shaped its initial research biases, didn't it? How did that impact the trajectory of AI research in those early decades?
Precisely. The assertion that intelligence could be precisely described aligns perfectly with McCarthy's deep mathematical background and his subsequent emphasis on symbolic methods and logical reasoning.
Right, symbolic AI. Can you maybe quickly break that down for us?
Sure, symbolic AI is basically about representing knowledge, explicitly using symbols and rules, much like humans use language and logic to reason. So instead of learning patterns from vast amounts of data like modern machine learning often does, it focuses on building systems that can manipulate these symbols and rules to solve problems through inference, through logical deduction.
Got it.
So this directed early efforts primarily towards these formal, logical, and symbolic approaches. And it led to significant breakthroughs in areas like expert systems and automated theorem proving. However, this also created a kind of historical tension.
How so?
Well, the inherent challenges in precisely describing all facets of human intelligence, particularly things like common sense and real-world adaptability, eventually led to the exploration and rise of alternative paradigms, like connectionism, the precursor to modern deep learning, and statistical machine learning.
Ah, okay, so it set up different schools of thought.
Exactly. It effectively set up the different schools of thought within AI that we still see echoes of today, highlighting an ongoing debate, really, about the most effective path to artificial general intelligence.
Now let's talk about the actual tools McCarthy created. His technical contributions were not merely incremental advancements, they were foundational innovations that defined the very tools and theoretical underpinnings of artificial intelligence. Starting with a programming language called Lisp.
Ah, Lisp, yes.
hmm
Lisp, an acronym for list processing, represents one of McCarthy's most enduring and impactful creations. Its development was a direct response to the emerging needs of AI research back then.
Right.
McCarthy began developing Lisp in 1958 at MIT, specifically because he wanted a language suited for symbolic computation, not just numerical calculations like Fortran, which was dominant then.
Okay.
He believed this was absolutely essential for manipulating abstract concepts, relationships between ideas, and even the very structure of programs themselves, which is what AI was fundamentally all about at the time.
And Lisp was significantly influenced by Alonzo Church's lambda calculus, wasn't it? Giving it this strong theoretical foundation for recursion and conditional expressions. That sounds like a true innovation, moving beyond the more rigid procedural languages of the day.
It absolutely was.
Mhm.
For those unfamiliar, Alonzo Church's lambda calculus is a powerful mathematical system for expressing computation purely through function application. Think of it as a kind of pure, elegant blueprint for how information can be transformed and combined, stripped down to its most fundamental operations.
Oh.
This gave Lisp its incredible flexibility and its capacity for building complex ideas from simple, recursive pieces. Now, while McCarthy initially proposed using M expressions, meta expressions, as its syntax, programmers pretty quickly adopted S expressions, or symbolic expressions.
Is expressions, right? Those parentheses.
Exactly, all those parentheses. They adopted S expressions due to their direct interpretability and elegant simplicity. This became Lisp's hallmark syntax. And crucially, it meant that Lisp could treat code as data, a revolutionary concept at the time.
Code as data, how did that work?
It meant the program could essentially manipulate itself or generate new code on the fly. Think about a program that learns it needs to be able to modify its own structure or rules based on new information. Lisp made that inherently possible. The first working Lisp interpreter was famously implemented by Steve Russell on an IBM 704.
Wow.
McCarthy then formally published Lisp's design in his seminal 1960 paper, establishing its theoretical foundations and cementing its place in computing history.
So the key insight here is that McCarthy didn't just build a language, he embedded a philosophical stance within its very architecture. This idea that intelligence isn't just about following fixed procedures, but about self-reflection and the ability to manipulate its own building blocks.
Exactly. Lisp's fundamental design, particularly its emphasis on symbolic expressions and this ability to treat code as data, was a direct reflection of McCarthy's belief that intelligence could be formalized and manipulated through logical symbols. It was a conceptual tool perfectly aligned with the symbolic AI paradigm. It provided the necessary computational infrastructure for researchers to explore and implement symbolic reasoning systems with just unprecedented flexibility.
That synergy sounds crucial.
It was. Lisp rapidly became the language of choice for programming AI systems, and really the dominant language for AI research throughout the 1960s and 1970s. Its flexibility, its expressive power, its capabilities for handling complex, nested data structures, these were highly valued. It allowed researchers to tackle problems of increasing complexity.
So it wasn't just academic.
Oh, no. It enabled the creation of sophisticated algorithms and complex data structures, even playing critical roles in things like NASA spacecraft systems. And beyond AI, Lisp significantly influenced the design of other programming languages like LGL60 by contributing concepts like recursion and dynamic typing.
Mm.
Although its widespread use in general programming declined somewhat in the 1990s, Lisp actually experienced a renewed interest in the 21st century, particularly in domains requiring high adaptability and metaprogramming capabilities.
Mm-hmm.
It just demonstrates its enduring design elegance.
And it wasn't just the language itself. Around 1959, McCarthy invented something called garbage collection methods as a solution to automatic memory management, which you mentioned was crucial for the dynamic nature of Lisp programs. Now, why was this seemingly small technical detail so important for AI and, well, for computer science in general?
Oh, it's far from small. This was a monumental contribution. Think about it. Symbolic AI systems, with their dynamic data structures, recursive operations, constantly changing knowledge bases, they inherently generate and discard huge amounts of memory during execution.
Right, constantly creating temporary stuff.
Exactly. Imagine a program trying to reason about a complex problem,
Yeah.
constantly creating and discarding temporary lists and data structures. Without automatic memory management, programmers would have been burdened with tedious, time-consuming, and notoriously error-prone manual memory allocation and deallocation.
That sounds like a nightmare.
It would have been. It would have significantly hindered the development of sophisticated AI applications, forcing researchers to spend more time on low-level system plumbing than on the higher-level logic of intelligence.
So garbage collection freed them up.
Precisely. This innovation, while a general computer science contribution, was a critical enabling technology. It allowed AI researchers to focus on the higher-level logic and algorithms of intelligence rather than constantly worrying about system details. Garbage collection was integrated into Lisp and has since become a standard feature in countless modern programming languages, Java, C#, Python, you name it. It totally transformed how software is developed.
McCarthy's vision extended beyond programming languages, though, to the fundamental way humans interact with computers. This led to his pioneering work on time-sharing systems.
Yes, time sharing. His conceptualization of this emerged around 1955. His vision was for an operating system that would allow each user to interact with the computer as if they had exclusive control, even if they were actually sharing a single, powerful, and very expensive machine.
Which they were, back then. Computers were huge and cost a fortune.
Exactly. In 1959, he formally described his scheme for general-purpose computer time sharing in a seminal memorandum, and his ideas directly inspired the development of several of the earliest time-sharing systems, including MIT's compatible time-sharing system, or CTSS,
CTSS, right.
which became operational in June 1962, as well as systems at BBN and Dartmouth. And while at Stanford, he also initiated the development of Thor, one of the first display-based time-sharing systems. That incorporated features now common in modern personal computers, like graphical displays and interactive commands.
This wasn't just a general computing improvement, was it? It feels like a profound game changer for AI.
Oh, absolutely. In the mid-20th century, computers were prohibitively expensive, scarce, and typically operated in batch mode. You submitted your program on punch cards and then waited hours, maybe even overnight, for the result.
Hard to imagine now.
Right. McCarthy's time-sharing concept directly addressed this bottleneck. It allowed dozens of users to interact with a single machine concurrently and instantly. This shift from slow batch processing to real-time interactive computing was as fundamental for early AI researchers as, say, having constant internet access is for us today.
Yeah, good analogy.
It transformed development from this slow, painstaking process into a dynamic, iterative one. It vastly accelerated the pace of experimentation and discovery in early AI labs.
The ability to share computational resources must have been essential for the iterative development, testing, debugging of those early AI programs, which often needed significant processing power and frequent adjustments.
Absolutely. This impact on AI infrastructure really underscores how foundational technological advancements, even those not directly related to AI algorithms, can profoundly shape a scientific field just by enabling research that was previously impractical.
And there were knock-on effects, too.
Huge ones. Crucially, CTSS, influenced by McCarthy, directly led to the creation of Project M at MIT, a major research initiative that further advanced interactive computing. And critically, time sharing was a fundamental building block for the eventual creation of the ARPANET.
ARPANET, the precursor to the internet.
Exactly. The ARPANET initially connected various time-sharing systems. It subsequently evolved into the internet we know today.
And it gets even more prescient, doesn't it? He literally saw the cloud coming decades before it was a thing.
It's incredible. In a remarkably prophetic 1961 speech, McCarthy was perhaps the first to publicly articulate the concept of utility computing.
Utility computing.
Yeah, suggesting that computing power in specific applications would eventually be sold as a public utility, much like water or electricity.
Wow. In 1961.
1961. This vision was extraordinarily forward-thinking, a true testament to his foresight. It extended beyond simply sharing a single machine to a paradigm where computing resources would be delivered as an on-demand service, accessible from anywhere, just like a public grid.
So like AWS or Google Cloud today?
Precisely. Now, while this idea receded in prominence by the mid-1990s, as personal computers became ubiquitous, it resurfaced after 2000 in new forms. And now we universally know it as cloud computing.
His colleague, Lester Ernest, confirmed this.
Yes, Ernest affirmed that the internet would not have happened nearly as soon as it did, except for the fact that John initiated the development of time-sharing systems, and that time-sharing concepts evolved into servers and ultimately cloud computing.
That's amazing.
This direct historical lineage to the internet and modern cloud computing demonstrates an almost unparalleled foresight. This conceptualization laid the philosophical and practical groundwork for the ubiquitous, scalable, and on-demand computing infrastructure that underpins virtually all modern AI development and deployment, including, the training and operation of massive language models and complex machine learning systems.
So his contribution here really transcends a specific AI algorithm. It's about creating the global environment in which AI could scale to its current unprecedented levels.
Couldn't have put it better myself.
McCarthy's intellectual rigor was perhaps most evident in his persistent efforts to formalize common sense and knowledge representation using mathematical logic. This was a cornerstone of the symbolic AI approach. And this brings us to his seminal advice taker concept.
Right, the advice taker. Proposed by McCarthy in his influential 1959 paper, Programs with Common Sense. The advice taker was this hypothetical computer program he envisioned.
Hypothetical, okay.
Yes, but hugely influential. It was one of the earliest proposals, maybe the first, to advocate for the use of formal logic, to represent information within a computer for the purpose of reasoning, rather than just storing it as raw data.
Okay, so reasoning, not just storing.
Exactly. McCarthy argued for programs that could manipulate common instrumental statements expressed in a formal language, most notably a part of predicate calculus. For context, predicate calculus is a system of symbolic logic used to express and reason about relationships between objects and properties. It enables more complex logical statements than just simple true-false propositions.
The core innovation of the advice taker was the idea that the program's behavior could be improved simply by giving it new advice, new statements in this formal language, without having to modify the program's internal code.
Right. This was intended to mimic human common sense and adaptability. Where we learn new facts and update our understanding without being reprogrammed every time.
That makes sense.
The advice taker aimed to automatically deduce a sufficiently wide class of immediate logical consequences from the information it was given, allowing it to infer new knowledge and plan actions based on what it knew.
So across his seminal works, from the advice taker to later contributions like situation calculus and circumscription, McCarthy consistently championed mathematical logic as the fundamental language and tool for representing knowledge and enabling reasoning in AI systems.
Absolutely. This was a deliberate philosophical and technical choice to move beyond rigid procedural programming, aiming for systems that could exhibit greater flexibility and common sense by inferring new knowledge from existing premises.
And this unwavering emphasis profoundly defined the logicist approach to AI, didn't it? Shaping symbolic AI for decades.
It really did. It laid a crucial foundation for logic programming and automated theorem proving. And it led to significant advancements in knowledge representation, automated reasoning, and expert systems, which were notably prominent in the 1980s and 1990s.
Then we have situation calculus, introduced in 1963, a logic formalism specifically designed for representing and reasoning about dynamic domains, so worlds that change.
Exactly. The main idea is that reachable states, which he called situations, can be defined in terms of the sequence of actions required to reach them. The ontology, the sort of building blocks, includes situations, actions, and fluents.
Fluents.
Fluents are properties whose values can change over time, like is the door open or closed? Is the light on or off?
Got it.
The formalism aims to allow a domain expert to axiomatize the relevant aspects of an application meaning, to precisely state all the known facts and rules, and then use automated reasoning mechanisms to draw conclusions about future states or the effects of actions.
And situation calculus was developed partly to address something called the frame problem.
Yes, the infamous frame problem,
Yeah.
which is essentially the challenge of specifying what doesn't change when an action occurs.
That sounds counterintuitive. Why focus on what doesn't change?
Well, think about it. Imagine an AI trying to plan a complex task, like making coffee. It needs to know that when it picks up the cup, the spoon on the counter doesn't suddenly vanish, or the color of the walls doesn't magically change.
Right. Most things stay the same.
Exactly. The frame problem is the immense challenge of efficiently representing all the things that remain constant after an action, without having to explicitly list every single one of them out every single time, because that would be computationally impossible for any complex world.
Ah, okay. I see the problem.
It's crucial for AI to develop a common-sense understanding of persistence in a dynamic world. And this was a significant theoretical challenge for logic-based AI systems.
And speaking of the frame problem, McCarthy developed circumscription between 1978 and 1986. This was a form of non-monotonic logic. Now that sounds interesting. What's non-monotonic logic?
It is fascinating. Unlike classical logic, where conclusions drawn from premises are always true and adding more information never invalidates previous conclusions, non-monotonic logic allows conclusions to be retracted when new information becomes available.
So it's more like human reasoning. We change our minds based on new facts.
Exactly. It's much closer to how we actually reason. The core idea of circumscription is to formalize the common sense assumption that things are as expected unless otherwise specified. It does this by, mathematically speaking, minimizing the extension of certain predicates, basically, assuming things don't have unusual properties unless you're told otherwise. A key application was formalizing the implicit assumption of inertia, that things do not change unless explicitly specified as an attempt to address the frame problem. It provides a formal framework for handling incomplete information and default assumptions, which are crucial for knowledge representation, expert systems, and decision support systems in the messy real world.
But it wasn't a perfect solution.
Well, it's important to note that McCarthy's initial circumscription solution, while a significant theoretical advancement and incredibly innovative, was later shown to lead to incorrect results in certain scenarios, like the famous Yale shooting problem, which is a classic AI puzzle about predicting the outcome of actions over time. This spurred further research. It really highlights the profound difficulty and subtlety involved in formalizing common sense and inertia, even for a mind as brilliant as McCarthy's.
Okay, so what does this frame problem mean for us today? And why was McCarthy's work on it so significant, even if his initial solutions weren't perfect?
Well, both situation calculus and circumscription were developed, in part, as direct responses to the frame problem. This challenge of efficiently representing what doesn't change when actions occur in a dynamic environment, without this explosion of frame axioms, which are explicit statements about what does not change.
Right, avoiding listing everything that stays the same.
Exactly. This problem exposed a deep limitation of classical logic in modeling real-world dynamics, where most things remain constant, but some key things change. The fact that McCarthy's initial circumscription solution, while innovative, was later shown to lead to wrong results underscores the profound difficulty and subtlety involved.
But identifying the problem was key.
Absolutely. Crucially, McCarthy's identification and formalization of this problem were arguably as significant as his proposed solutions, because it highlighted that simply adding more facts to a knowledge base wasn't enough. AI systems needed a principled and efficient way to handle assumptions, defaults, and the persistence of facts in a changing world.
A challenge that's still relevant.
Very much so. It continues to influence research in knowledge representation, automated planning, and reasoning under uncertainty, even today. It really pushed the field to confront the complexities of real-world knowledge.
Moving on from his direct technical contributions, McCarthy also understood that for these ideas to truly flourish, AI needed more than just brilliant minds. It needed dedicated homes. This brings us to his crucial role in establishing AI research hubs.
Yes, the institution building.
In 1959, he, alongside Marvin Minsky, co-founded the Artificial Intelligence Project at MIT. This laboratory quickly became a preeminent center for pioneering research across a wide spectrum of AI subfields, robotics, theory of computation, common sense reasoning.
Right, and he also played a significant role in motivating the creation of Project MC at MIT, which was a massive interdepartmental computer science research program.
Then, upon moving to Stanford University in 1962, McCarthy established what became the Stanford Artificial Intelligence Laboratory, or SAIL, in 1972.
Legendary place.
It received substantial funding from DARPA, the Defense Advanced Research Projects Agency, including a $1 million computer facility, which was a huge sum for research in those days.
Absolutely huge.
It rapidly distinguished itself as a leading global center for AI research, known for its vibrant community of very bright faculty, students, and staff.
What an incredible legacy of talent and innovation must have come out of there. For many years, SAIL maintained that friendly rivalry with MIT's Project Mank, fostering a healthy competitive environment that spurred innovation and ensured ideas were rigorously challenged and refined.
And under McCarthy's leadership, SAIL became this crucible for foundational work in areas that are now just ubiquitous in our daily lives. Think about graphical user interfaces, computer typesetting and publishing, early speech recognition systems, expert systems that revolutionize specific industries, computer vision, robotics, even computer music.
The breadth of innovation is staggering, isn't it?
It really is.
And again, McCarthy's impact extended beyond individual inventions. He was a master institutional builder. His co-founding of the MIT AI project and, more significantly, his establishment and leadership of SAIL at Stanford, they demonstrate this keen understanding that sustained, large-scale progress in a nascent field like AI requires dedicated, well-resourced collaborative environments.
These labs attracted top talent from around the world, secured crucial government funding.
Exactly. And they provided the necessary infrastructure for diverse and ambitious research projects. This foresight in creating these AI hubs was instrumental in transitioning AI from theoretical ideas to practical research, creating the very ecosystem for AI to flourish, attract investment, and eventually commercialize.
And it wasn't just academic research, it spun out into industry.
Massively. The lab was highly successful in producing numerous PhDs and graduates who went on to become leaders in the field. It evolved into a hotbed of entrepreneurial activity, as we mentioned. This directly led to dozens of direct and indirect corporate spin-offs, influencing companies that would become titans of the tech world like Microsoft, Sun Microsystems, Amazon.com, Cisco Systems. This was the foundation of an industry.
His influence was also profoundly felt through specific projects and philosophical inquiries that pushed the very boundaries of AI, both practically and conceptually. For example, McCarthy and his team at Stanford developed a chess program, one of the earliest complex game-playing AIs.
All right, the chess program.
In 1966, this program famously competed against counterparts in the Soviet Union, a significant cultural moment during the Cold War, actually. While McCarthy's program lost 2 games and drew 2, this was still a significant early demonstration of AI's capability in complex strategic domains. It showcased the power of symbolic methods in a well-defined problem space.
These projects were practical applications, vital testbeds for the symbolic AI paradigm McCarthy championed. And while they demonstrated impressive capabilities for their time, I mean, a computer playing chess at any level back then was a marvel, they also implicitly highlighted the inherent challenges.
Challenges like?
Challenges of scaling purely symbolic methods to complex, open-ended, real-world tasks that demand extensive common sense or fine-grained perception or intricate physical interaction. The chess program, for instance, relied heavily on exhaustive search and logical evaluation within a very well-defined domain. It pushed the computational boundaries of symbolic systems to their absolute limits.
Beyond chess, at Stanford, McCarthy's lab also engaged in groundbreaking research on early versions of a self-driving car. Imagine that, decades before it became a mainstream pursuit.
Self-driving cars in the 60s or 70s, that's incredible.
Yeah. And SAIL initiated a hand-eye project, which utilized video camera information to guide a robotic arm in assembly tasks, foreshadowing modern industrial robotics and computer vision. He was even involved in the development of Elephant 2000, a programming language intended to have semantic features based on speech acts, exemplifying his continued interest in the intersection of language, logic, and computation, trying to make machines understand the meaning behind our words, not just the syntax.
These early tangible AI projects served as vital test beds for McCarthy's logic-based approaches. Their successes validated the symbolic paradigm for specific problem types, while their limitations provided crucial feedback. And this feedback directly informed McCarthy's later theoretical work on common sense reasoning and non-monotonic logic.
And maybe push towards other approaches, too.
Absolutely. It also contributed to the eventual exploration of alternative AI paradigms like machine learning and connectionism, precisely to address the gaps in purely symbolic reasoning. It was this constant cycle of theory, implementation, refinement, and identifying limitations.
Could a thermostat really have beliefs? This intriguing, almost whimsical question actually stems directly from McCarthy's 1979 article, Ascribing Mental Qualities to Machines.
Ah, yes, that famous paper.
It controversially argued that even simple machines like thermostats could be said to have beliefs, for instance. The thermostat believes the room is too cold and acts accordingly. This article famously served as the catalyst for philosopher John Searle's influential Chinese room argument.
Right, the Chinese room. Still debated today.
Exactly. A thought experiment that remains central to discussions about strong AI and the nature of machine understanding. It asks if a machine truly understands, or is it just manipulating symbols without any real comprehension?
Furthermore, McCarthy's willingness to delve into these profound philosophical questions about machine consciousness, free will, the ascription of mental qualities to machines,
Yeah.
this was not a tangential interest for him. It was an integral part of his AI vision.
So he wasn't just building machines, he was probing the very nature of intelligence itself.
Precisely. His 2001 short story, The Robot and the Baby, humorously explored whether robots should, or could, simulate having emotions, pushing the boundaries of what machine intelligence might entail. His public engagements, like his debate with John Searle over the Chinese room argument, were early, high-profile discussions of the very questions that now lie at the heart of contemporary AI safety, ethics, and alignment research.
So he was asking the big ethical questions way back then.
He really was. This demonstrates that a comprehensive understanding of AI's foundations must necessarily include its philosophical dimensions, a realm McCarthy actively shaped and whose questions remain profoundly relevant today as AI becomes more sophisticated and autonomous.
So looking at his entire career, John McCarthy is unequivocally recognized as one of the founding fathers of artificial intelligence, particularly for his instrumental role in establishing and advancing the symbolic AI paradigm.
Without a doubt. His work consistently emphasized the use of formal logic for reasoning in AI systems, and he promoted the pursuit of generality in fundamental AI research areas, including robotics and natural language understanding.
A cornerstone of his approach was that strong advocacy for representing knowledge in declarative sentences, typically within a logical language, rather than embedding it directly within the program code.
Right, the declarative approach. This inspired a vast number of researchers and led to the development of many practical AI applications. His pioneering work on non-monotonic logic and the development of circumscription significantly enhanced the AI field's ability to reason under uncertainty and handle incomplete information, a crucial capability for any intelligent system operating in the real world.
McCarthy's overarching vision of AI as an extension of human intelligence, and his foundational conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. These continue to serve as guiding principles and ambitious goals for current AI advancements, even for paradigms far removed from his original symbolic approach.
And what's fascinating here is that while the current AI landscape is largely dominated by statistical machine learning and deep neural networks, McCarthy's foundational work in symbolic AI remains profoundly relevant.
How so, specifically?
While many of the challenges that McCarthy addressed, like common sense reasoning, handling incomplete information, achieving explainability, these are still active and critical research areas. This is particularly true in the quest to enhance the robustness, trustworthiness, and reliability of large language models, LLMs, and other data-driven systems.
Because LLMs can sometimes lack common sense or logical consistency.
Exactly. These modern systems often excel at pattern recognition, but they can struggle with logical consistency or truly understanding the meaning behind the data. And that's precisely where McCarthy's insights into logic and knowledge representation offer potential solutions.
So this raises an important question. How do these seemingly disparate approaches, McCarthy's symbolic logic and today's data-driven AI, actually connect? Are they completely separate?
Not necessarily. Concepts like generative AI and large language models can, in fact, be seen as direct descendants of the principles McCarthy helped establish, particularly his early vision for systems that could simulate human-like conversations and dynamically generate content. The advice taker, in a very rudimentary way, was about a machine learning from new facts and generating new deductions.
Interesting connection.
Absolutely. And his foundational ideas on knowledge representation, stemming from the advice taker, laid the groundwork for modern knowledge-based systems, expert systems, semantic networks, and sophisticated knowledge graphs.
Knowledge graphs, right? Those are becoming important again.
Very much so. These are increasingly used today to augment and provide structure to data-driven AI, giving it a factual grounding that it often lacks. We see the resurgence of knowledge graphs, which are direct descendants of his ideas on knowledge representation, as a means to ground and augment neural networks. It demonstrates a powerful convergence of symbolic and statistical approaches.
So his legacy isn't just historical.
Not at all. It indicates that McCarthy's legacy represents a complementary and increasingly recognized paradigm.
And let's not forget the cloud connection we talked about. McCarthy's early and prescient vision of utility computing, enabled by time sharing, has fully materialized in the form of cloud computing.
Right, and that ubiquitous infrastructure is now absolutely essential for the massive computational scale and accessibility required for training and deploying contemporary AI models, from the smallest startup to the largest research lab.
Without his foresight there, the practical reality of modern AI might look very different.
It really might. And his philosophical explorations into machine consciousness and free will, which once seemed purely theoretical, find very real practical expression in the development of modern agentic AI systems that exhibit remarkable autonomy and decision-making capabilities.
So the trend towards hybrid AI.
Exactly. The contemporary trend towards hybrid AI, which seeks to combine the strengths of symbolic reasoning like logical consistency, explainability, robust knowledge representation, with the pattern recognition capabilities of neural networks, directly validates the ongoing importance of his foundational contributions.
So it provides a framework for addressing the limitations of purely data-driven AI.
Precisely. Particularly in areas requiring robust reasoning, ethical considerations, and verifiable knowledge. It's really about bringing the best of both worlds together, and McCarthy's work is a vital part of that symbolic foundation.
As we wrap up this deep dive, then, it's just abundantly clear that John McCarthy's impact on artificial intelligence is multifaceted and profound. It extends from its very nomenclature, the name itself, to its core theoretical and practical underpinnings. He was a true visionary, who not only defined the field, but also provided so many of the essential tools and frameworks that enabled its growth from, well, a daring idea into a global phenomenon.
His legacy is evident everywhere. In the widespread use of symbolic programming paradigms influenced by Lisp, the ubiquitous nature of time-sharing and cloud computing that powers our digital world, and the ongoing pursuit of robust knowledge representation and common-sense reasoning in AI systems. His intellectual curiosity, his insistence on formal rigor, and his foresight in establishing dedicated research institutions really cemented his place as a true pioneer whose influence continues to shape the future of technology.
So if we connect this to the bigger picture, as AI continues its rapid evolution, particularly with data-driven models like large language models pushing boundaries and sometimes exhibiting unexpected, maybe even problematic behaviors, what important question does McCarthy's enduring legacy of formal logic, knowledge representation, and that quest for true common sense reasoning raise for the future? How do we build truly robust, ethical, and reliably intelligent machines? Are we destined to fully merge his symbolic approach with today's statistical powerhouses, or will one always reveal the limits of the other?